Um, okay, perfect. So today's speaker is Emily Adlam, who is a professor at Chapman University. Emily received her PhD from Cambridge and did a postdoc at Western University prior to her current position. She's interested in the foundations of quantum mechanics and the philosophy around that. And today she's going to tell us about entropy bounds, probably in a way we're not used to thinking about. So please go ahead.
Great. Thank you very much for the invitation. It is very early here, so I'm not entirely awake, but I will do my best. I want to talk about this question, entropy bounds epistemic. And I've been told that when papers have a question in the title, the answer is usually no. In this case, the answer is going to be, I don't know. I think both answers are sort of plausible. What I want to do is not sort of argue for one particular position, but sort of suggest why I think there are these two different possible interpretations, talk about some points in favor of each of them, and then perhaps at the end, some of you can tell me what you think the answer is. So I'll give some brief background on entropy bounds. I'll then talk about the general problem of learning about physics inside a region of spacetime. I'll use that to motivate the possibility of an epistemic view of the bound, which I'll contrast with the ontological view. I'll talk briefly about how current knowledge of entanglement entropies might contribute to this question. And finally, I'll talk about how all of this connects to gravity. So the story of entropy bounds begins with the Bekenstein-Hawking entropy, the entropy proposed by Bekenstein and Hawking for a black hole, which is given by S equals the area over 4gh bar. So at the time of being proposed, this was fairly speculative, but we now have a pretty good degree of theoretical evidence that this entropy is probably right. It matches up with other things we understand about black holes. But this entropy for black holes has consequences for what we can say about the entropy of other regions of space-time as well. That's because if you lower some arbitrary system into a black hole, that's going to change the entropy and area of the black hole. And if you want the black hole to continue obeying the Bekenstein-Hawking entropy relation, then the entropy of that system had better be less than or equal to 2 pi ER over h bar. And it turns out that for a weakly gravitating system, this reduces just to the simple formula S is less than or equal to A over 4gh bar. Now that is quite a striking and interesting result and led to the speculation that perhaps, in fact, that bound is just true for any region of spacetime whatsoever. Perhaps regions of spacetime just have an entropy which is proportional to their surface area. Now, if that were true, that would be pretty surprising. You might naively expect that the entropy of a region of spacetime should scale with its volume rather than its surface area. We can, to some extent, explain why this happens by noting that if you put too much mass into a region of spacetime, it's going to collapse to form a black hole, and thus there are sort of fewer states available in a region of spacetime than you would naturally expect. But nonetheless, that still doesn't explain why it scales exactly with the surface area rather than the volume. That seems like a sort of striking regularity, which is in need of explanation. Now, it turns out that the strong entropy bound is not, in fact, true universally in our universe. It can be violated in regions of spacetime where the structure of spacetime is undergoing some particularly rapid change. So in cases of cosmic inflation, say, gravitational collapse, and so on. But it turns out that there is a covariant generalization of the bound, which, as far as we can tell, does appear to be true for our universe, at least at the sort of quasi-classical level. The covariant entropy bound says that S is less than or equal to A over 4gh bar again, but now we're going to define the interior of the region slightly differently. So rather than looking at the interior of the surface on the same space-like slice, we're going to define the interior of the region using a light sheet. So we define light sheets by looking for sets of null geodesics leaving the surface orthogonally. We look at those sets and find sets with 0 or negative expansion. Those sets define the light sheet, and so we just trace the geodesics from the surface until they meet a caustic or a singularity, and the area they traverse is the light sheet. So that's easiest to illustrate by an example. If you think about a sphere, the sphere is going to have 4 different classes of null geodesics leaving its surface orthogonally. You can have them going out of the surface into the future, out of the surface into the past, into the sphere into the future, or into the sphere into the past. So clearly the geodesics going out of the surface are going to be getting further away from each other over time. So they have positive expansion, but the ones going into the sphere are getting closer to each other as they move further away from the surface. So they have 0 or negative expansion. So it's those 2 classes, the ones going into the sphere, which define light sheets, and we simply follow those rays until they meet at the center of the sphere. In that example, you could also see that the covariant entropy bound is going to reduce to the strong bound in many cases, because if you think about the area traversed by those light sheets, they are going to traverse just the entire interior volume of the sphere. So as long as nothing too strange is happening inside in terms of the structure of space-time, you're going to get the entropy on that light sheet is just going to be the same as the entropy on any space-like slice in the interior. So in that kind of case, the 2 bounds kind of coincide. They just differ in these special cases like cosmic inflation, gravitational collapse, and so on. And in those special cases, the covariant entropy bound seems to be right. The strong entropy bound is violated. So because the bounds are so closely related, the covariant bound is surprising for much the same reasons as the strong entropy bound. There seems to be less entropy around than you would perhaps naively expect, and the fact that we get the scaling with exactly the surface area rather than the volume seems surprising, seems something we would like to understand better. So in view of this bound, various proposals have been made that what it's telling us is that the number of degrees of freedom in regions of space-time is perhaps less than you would naturally expect, and seems to scale with the surface area rather than the volume. We want to be careful with that claim because entropies don't straightforwardly correspond to a count of a number of degrees of freedom. Arguably, sometimes the information theoretic Shannon entropy can be regarded as counting the number of sites for information storage or something like that. But the entropies that are involved in the covariant bound are presumably thermodynamic entropies. The Bekenstein-Hawking entropy does seem to pertain to thermodynamic entropies, and the covariant bound was kind of derived from there, so it's probably talking about the same kind of entropies. And thermodynamic entropies certainly don't always correspond to a number of degrees of freedom. If you're looking at the Boltzmann entropy, for example, the Boltzmann entropy of a system is going to be given by the number of microstates compatible with the most likely macrostate, and that is not going to be equal to the number of degrees of freedom in the system, unless it should happen that there is some macrostate which is compatible with all of the microstates. So it's not in general true that thermodynamic entropy exactly corresponds to the number of degrees of freedom, but in some cases there may be some relationship between them. In many systems, the Boltzmann entropy is going to be pretty close to, if not exactly equal to, the number of degrees of freedom. The other concern you might have here is that entropy or thermodynamic entropy is often understood as being observer dependent. That's because the value of the entropy is going to depend on how you sort of divide the state space up into macrostates, and that's typically done by appeal to features of the observer, like what properties they can distinguish, what capabilities they have to interact with the system, and so on. And you might think that if entropy is, in fact, an observer-dependent quantity, the entropies couldn't possibly tell us about some sort of observer-independent feature of the system, such as its number of degrees of freedom. With that said, Flanagan, Maroff, and Wald do anticipate that objection, and they argue that this apparent tension is kind of diffused by the fact that what we're dealing with the entropy bound is not a specific individual entropy, rather it is a universal bound on all possible entropies. So it could be the case that all of the individual entropies you might define are dependent on properties of the observer, but nonetheless, this universal bound on the maximum value of those entropies is not observer dependent, and thus that bound could reflect a feature like the number of degrees of freedom, even though the individual values of the entropy are not observer independent in that way. So with those caveats in mind, let's for the moment accept the idea that the entropy bound is telling us something about the number of degrees of freedom in some region of spacetime. The question then is, what is the region of spacetime for which it is counting the degrees of freedom? There are sort of two obvious options here. One is to say that the bound is counting the number of degrees of freedom on the light sheet. That's the part of spacetime on which we're calculating the entropy after all. So that seems a natural place to look for those degrees of freedom. But a number of people have suggested that actually the bound is just counting the number of degrees of freedom on the surface, telling us that the number of degrees of freedom on the bounding surface is given by A over 4gh bar. Now, if the number of degrees of freedom on the surface is given by A over 4gh bar, that seems in many ways very unsurprising. Certainly, if you had any reason to think that the number of degrees of freedom on the surface is finite, you would probably naturally be inclined to suspect that it should be proportional to the surface area. And thus, if that's the right bound for the surface area, that would be not perhaps as exciting and interesting as the covariant bound originally seemed to be. If the covariant bound is just telling us something about degrees of freedom on surfaces being proportional to areas, it's much less sort of radical and innovative than it originally seemed. On the other hand, if the surface postulate were the right formulation, it's not clear why we would have to distinguish between the strong and covariant versions of the bound. Those versions are the same, after all, in what they say about the surface. They differ just in how they define the interior of the region. And if the bound were just telling us something about degrees of freedom on the surface, it's kind of not clear why it would matter how you define the interior of the region. So that suggests that perhaps we should think we are really counting degrees of freedom on the light sheet and not just on the surface postulate, not just on the surface, in order to make sense of the fact that it matters how you define the interior region. So there are in some ways reasons to think that maybe both of these statements are correct. We would expect anyway that the number of degrees of freedom on the surface should be A over 4gh bar. The fact that the interior region matters gives us reason to think that the number of degrees of freedom on the light sheet is maybe also equal to A over 4gh bar. But if they are both correct, why on earth do they stand in this particular relation? It surely can't be a coincidence that the number of degrees of freedom on the light sheet is apparently equal to the number of degrees of freedom on the surface. If that is right, there's got to be some explanation for it. And there seems to be something important going on in terms of the relationship between those two areas. So I just want to suggest...
You didn't mention, I mean, there are model calculations in the string theory context where you count the number of degrees of freedom that are brought together to form the black hole, which coincides with that computation of the area over 4gh bar.
Yes. Mm-hmm. So we do have some potential explanations for this bound in the case of black holes. But the covariant bound isn't true just for black holes. It seems to be true for all regions of space-time everywhere. So the question I want to address is not just about why is that the number of degrees of freedom in a black hole, but also why is that apparently the number of degrees of freedom in any region of space-time? Because if that is true, that seems to be telling us something important about space-time and its properties. Does that make sense?
Yeah, okay. All right, let's continue.
Okay, so I want to suggest one way in which the degrees of freedom on the surface and the degrees of freedom in the interior could be related to each other. So to do that, I want us to think a little bit about the problem of studying physics inside some region of spacetime. And to think about that, let's imagine the following thought experiment. Suppose I give to you a sphere which is opaque, and I tell you that there is some new physics going on inside the sphere, something totally different to any known physics. So your job is to try to find out something about what that physics is, but you're not allowed to look inside the sphere. You're going to have to do this by using some LEDs that I have embedded on the surface. So let's imagine the sphere is covered in a grid of N LEDs. The LEDs are going to light up when they receive a signal from the interior. And that's going to be your only access to the physics going on inside this region. So what are you going to do to try to learn about the physics in this region? Well, you'll probably do something like take a look at the pattern of illuminations of the LEDs over time, perhaps try to make a record of that, perhaps look for patterns in those in those illuminations over time, and perhaps write down something like a time evolution law describing how the illuminations change over time. And you might well just stop there. If you do stop there, what you will have done is described the sphere with a state space of n bits corresponding to the n LEDs. So in that case, you have a sort of clear bound on the state space, which is equal to the number of LEDs on the surface. You might perhaps try to do something a little more complicated. You might try to make some inferences about what kinds of things happening inside the sphere could explain the illuminations you have seen on the outside of the sphere. But because you can still only see sort of n bits of information about the interior per sort of unit time, you're still in some sense quite likely to end up with a description assigning n degrees of freedom to the interior as well. Additional degrees of freedom you might add would sort of seem to be in some sense superfluous and could be replaced with just sort of randomness of some kind. So even in that case, it seems quite likely that you would end up with a description and assigning n degrees of freedom to the interior. I don't want to say it's totally impossible you could end up with a description with more than that. It is possible that by sort of accumulating information over time, you might eventually feel that you have learned more about the state space of the interior region. But certainly it would be in no way surprising if in this situation you ended up assigning the interior of the sphere a state space of n bits. And moreover, that is true basically regardless of how many degrees of freedom there really are inside the sphere. That fact about the state space is not a feature of the sphere, it's a feature of your epistemic access to it and your ability to learn about what's going on inside the sphere. So the point of this thought experiment is that in some sense, we are sort of always in this situation when we're trying to learn about physics inside regions of spacetime. We don't access the systems that we're trying to study directly. We access them through their bounding surfaces, and thus the information we can get about them is going to be limited by the rate at which information can pass out through that bounding surface. So in particular, if the surface postulate is true, if the number of degrees of freedom on a surface of spacetime has a bound proportional to the area, then there are also going to be bounds on how much information we can extract about a system per unit time in a similar way to the LED situation. You're sort of limited in terms of the information you can get out at any one moment. So that sort of suggests one way in which the covariant bound could be related to the surface postulate. It could be that rather than the covariant bound telling us the true ontological number of degrees of freedom on a light sheet, it's telling us something about the amount of information we can extract about the light sheet through its bounding surface. So that suggests an interpretation of these bounds, which were in terms of a reflection of our epistemic limitations, rather than necessarily intrinsic features of these physical systems in and of themselves. Now, you might at this point worry that I have used an example which is perhaps more friendly to the epistemic interpretation because I have described a case with a closed surface like a sphere, whereas, of course, the covariant bound is also supposed to apply to open surfaces like a sheet. And you might think the epistemic interpretation is less plausible in the case of a sheet, since the information doesn't have to pass through the sheet to get to me. It could go around the outside instead. And with that said, of course, if I'm going to extract any useful information from signals reaching me that go around the outside of the sheet, I'm going to need to know the content of the spacetime in the region around the outside of the sheet. Otherwise, I won't be able to interpret that information. So really what we should do in that case is sort of extend the sheet such that it covers the whole region from which information is reaching me. And then in that case, it is true that all the information that arrives in me is going to have to pass through this extended sheet. So I think even in the case of a sheet, the epistemic interpretation is still somewhat plausible. You can potentially think about the covariant bound as saying something about our abilities to get information about these regions as observers observing them from the outside. So this sort of points to an important role played in physics by surfaces and the way in which they kind of mediate our access to the systems we're trying to study. A number of people have sort of observed that there is this important role for surfaces. Crane, for instance, notes that if we divide the universe into system and observer, the observer doesn't directly measure the system. They measure the part of it which impinges instantaneously on them. So the bounding surface is what they have access to. That motivates his topological formulation of quantum gravity. Euclid's general boundary formalism is also quite strongly focused on trying to understand the properties of surfaces and transitions between them, because the surfaces are what we access experimentally. And May notes that we can think of holography as saying something about surfaces as well, and we can think of it as something like the requirement that asymptotic tasks possible using the bulk dynamics should coincide with tasks possible using the boundary, which of course is what you would sort of naturally expect if we're looking at physics developed by observers who are accessing systems from the outside and doing tasks using boundaries and not bulks. So with that in mind, I wanted to distinguish a couple of different possible interpretations of the covariant bound. So here I'm going to be assuming that the covariant bound is saying something about the degrees of freedom somewhere, and having a look at different ways we could interpret that. So the epistemic interpretation, based on the suggestion I've just made, says that the real number of degrees of freedom on a light sheet may be greater than the amount specified by the covariant bound. So there's sort of pragmatic and positive versions of that view. The pragmatic version would say something like, there might be such extra degrees of freedom, but they're not going to have any impact on anything we can observe, so let's just get on with physics as if they're not there. A more positive version would say it might be important to take those extra degrees of freedom into consideration when doing physics, even though we can't directly observe them. By contrast, the ontological interpretation is perhaps the more traditional interpretation of the bound. It tells us that the bound is counting the true number of ontological degrees of freedom on a light sheet. Again, you can sort of just distinguish a pragmatic version or a positive version. The pragmatic version would say something like, we can't have any information about degrees of freedom beyond the bound since we couldn't access them, so let's just assume there aren't any. The positive version would commit to the covariant bound being something like a fundamental constraint or a reflection of aspects of fundamental ontology. So it's not just a pragmatic limit, it tells us something profound about the nature of our reality. So with that classification in mind, we can distinguish between different possible interpretations and how they are espoused by various different physicists. So there hasn't been a great deal of discussion of interpretations of the covariant bound specifically, but there has been a lot of discussion of how you should interpret the Bekenstein-Hawking entropy. And we can see a tendency towards some epistemic views in what some physicists have had to say about the Bekenstein-Hawking entropy. So in particular, a number of physicists seem to hold what I've called a pragmatic epistemic view of the Bekenstein-Hawking entropy, where they sort of acknowledge that there may in some sense be more entropy present than the bound counts, but they don't consider it relevant to physics once it's gone beyond the horizon. So the idea that entropy vanishes when it passes behind the event horizon seems to reflect that kind of epistemic take on the bound. The system presumably doesn't vanish. Its mass is needed to drive area increase, but we don't sort of include it in the count of ordinary entropy because it is considered out of sight, out of the world, or at least out of physics. So that's a sort of pragmatic epistemic view. But there are also some physicists who have espoused more sort of positive epistemic views of the Bekenstein-Hawking entropy, so including Smolin, Sorkin, and Ravelli. So for example, Ravelli argues that the page argument concerning information loss is based on the fact that if the number of black holes states is determined by the area, then as the black hole shrinks, there aren't enough black states inside anymore to be entangled with the Hawking radiation, and that is where the paradox sort of comes from. Whereas if you allow that there might be more states available in the black hole than the Bekenstein-Hawking entropy suggests, if, for example, you say that entropy is reflecting an epistemic limit rather than an ontological limit, then Ravelli says the page argument for the information loss paradox fails. You may or may not believe Ravelli's argument here, but the point I want to make is just that Ravelli does seem to be holding an epistemic view where he allows that there may be additional states in the black hole and they're just not accessible from the outside. The contrasting option is the ontological view. This, I think, is the idea most commonly sort of articulated when people do explicitly discuss the interpretation of the covariant bound. So Bousseau himself, who came up with the covariant bound, does seem to hold what I've called a positive ontological view of it. So he argues that the simplicity of the bound, in addition to its generality, makes the case for its fundamental significance compelling. So they seem to think that it is a fundamental fact about the structure of space-time that it has this limitation on the number of degrees of freedom proportional to the surface area. However, I think the fact that there are possible epistemic interpretations of the bound does perhaps raise questions about ontological interpretations of the bound. You might worry that what's going on here is that we are looking at our physics and mistaking the consequences of an epistemic limitation for ontological facts about the world. So it's not clear sort of how you could really prove conclusively that what's going on here is a count of the real number of degrees of freedom rather than the ones that are accessible to us. In particular, the ontological view still has to contend with the fact that it seems like it's sort of a coincidence that the number of degrees of freedom on the light sheet seems to match the number you would expect there to be on the bounding surface, whereas we've seen that this relationship can be explained in the epistemic situation. So unless the ontological approach can sort of come up with a compelling explanation for why that relationship should hold, that does seem to give the epistemic interpretation a bit of an edge. Okay, so thus far I've talked about the entropies as if they are entirely classical. Sorry.
If I can interrupt to clarify.
Yes, by all means.
I usually think of entropy in two different contexts. One in which I'm not sure whether it's epistemic or I think it's ontological, is the entropy as defined by the canonical ensemble.
Yes.
And you are, as far as I can see, you're floating from the canonical to the microcanonical ensemble. That mental changes happening in the background from the way
Yes. So I mean the entropy
that suggests that you have an equivalence of ensembles floating in there. So which means that both of them can be true at the same time.
Interesting.
So I'm not quite sure how you're thinking about this, because to me the counting is the microcanonical ensemble, whereas Bekenstein-Hawking, clearly there's a temperature there, and you're getting it by a Legendre transform from the temperature to associated with a canonical ensemble.
Yes. So, I mean, in general, the entropies featuring in the covariant bound are not calculated using sort of statistical mechanical methods. The calculation, when we try to show that the bound is correct, the calculation just relies on treating entropy as a fluid, which sort of follows the curvature of space-time in the ways you would naturally expect. And so, in general, we don't necessarily know exactly what the degrees of freedom relevant to the bound are, or what ensemble is to be used here. This is all sort of
implicitly, the way you're talking, it sounds like it has to be microcanonical.
Well, I think the assumption people are making is that the entropies we have calculated at the sort of more macroscopic thermodynamic level are corresponding to a number of degrees of freedom in the standard statistical mechanical sense, and so they are the claim that people have made is that these entropies do tell us
our standard microcanonical senses, and they don't always agree.
Sorry, what was that?
Both of the descriptions I've given, the canonical or microcanonical for a system, they don't have to agree, and they only agree if you have an equivalence of the ensembles, which is only true in thermodynamic limits. So you're dealing really with an infinite number of degrees of freedom. So I'm not quite. It seems to me that you need to make a choice, and that the choice you've made is that you are dealing with microcanonical implicitly.
So, I mean, the way that these calculations are done, no ensemble is used. The calculations are sort of done entirely at a sort of higher level thermodynamic scale, and then there's some assumption that presumably that maps onto some kind of ensemble, and you can think of it as counting the number of degrees of freedom, but that's not an explicit calculation that people do. This is done at the higher level.
Yeah, I don't really understand that, but you can go on, because I'm not going to.
Sure. I mean, I'm not necessarily saying this is a correct way to think about it, but I'm sort of trying to understand if it is true in some sense that the entropy bounds should be thought of as counting a number of degrees of freedom, whatever story you're going to tell about the nature of the degrees of freedom involved in that ensemble is then going to have to correspond to degrees of freedom in some region.
Okay.
Great. Okay, so thus far I have talked about the entropies involved in the story as, roughly speaking, classical entropies, but presumably in some sense the entropies are ultimately going to be quantum in nature. You would expect them to be von Neumann entropies, and certainly when we did give proofs of the bound in the context of quantum field theory, the entropies involved are von Neumann entropies. Moreover, assuming that we're dealing with a sort of unitary only interpretation of quantum mechanics, it's likely that the entropies are entanglement entropies, and thus that's potentially going to change some of the interpretative things I've just said. With that said, because what we're dealing with is not the value of any specific individual entropy, but the value of a universal upper bound on the entropy, in some sense, some of the interpretative claims are to some degree going to be independent of the specific nature of the entropies involved. We're interested not in how to interpret the individual entropies you might assign to the region, but rather how to interpret the existence of a universal bound on any possible entropy. So to some extent, therefore, it shouldn't matter too much how you interpret the entropies involved. And indeed, I think in the case of von Neumann entropies, both the ontological and epistemic interpretations of that bound are still possible. Of course, the dimension of a system's Hilbert space is going to be an upper bound on its von Neumann entropy. So a very plausible way to get a source for a universal bound on the entropies is just to say that bound comes from the dimension of the system's Hilbert space. That is an ontological interpretation of the bound, which says that that bound is counting the real number of degrees of freedom available to us as encoded in the Hilbert space. On the other hand, entanglement is also closely associated with knowledge in a certain sense. Certainly in unitary quantum mechanics, everything I can know about a system is going to take the form of entanglement between my brain and the system. So that observation points to the possibility of an epistemic interpretation, where you would think of the bound as giving some kind of limit on the degree of entanglement we can form with certain regions, and thus telling us something about how much information we can get about them. Indeed, I think in some ways the possibility of working in terms of entanglement entropies makes the epistemic account a little bit stronger, because one worry you might have had about the epistemic interpretation would be that if I'm sort of standing on the outside of a region of space-time observing it over time, I can gather more and more information over time, and so eventually I'll arrive at enough information about the interior to assign it a state space greater than the number of degrees on the surface. Whereas the entanglement entropy bounds sort of refer to the amount of entanglement accrued over time already. So they've sort of already built in the possibility of additional information being accrued over time, and they have ruled out that possibility. So in that sense, the entanglement entropy bounds, I think, plug a potential loophole in the epistemic account. So in particular, if you're looking at the idea that the entropies involved in the bound are von Neumann entropies or entanglement entropies, it's perhaps very tempting to say that we can explain the bound by appealing to area laws for the entanglement entropy. That's because it can be shown in the context of QFT that in many cases, the von Neumann entropy of a system will scale with its surface area and not its volume. So you might be tempted to say that is why we get the covariant bound, that is coming from some kind of area law. Now, there are a couple of limitations that we'd have to overcome before we could use the area laws to explain the covariant bound. One is that the area laws are not universal. They typically only apply to the ground state. There are reasons to think that there are theorems which suggest that excited states in quantum field theory will have the same structure as the ground state. if it's a continuum quantum field theory, and that might suggest that similar laws should apply in excited states as well. But that does only apply if the theory is a continuum theory, and it's not obvious that's not what we're dealing with in the actual world. In addition, the area laws apply to the sort of leading term for the von Neumann entropy. There will also be subleading terms, which plausibly can contribute to going above the bound in some cases. In addition, the way in which the area laws come out will depend on our choice of UV cutoff. And so you'd have to find some sort of justifiable way of making the cutoff, which gives you the right result. The final issue is that area laws are typically defined on a sort of space-like hyperplane. That's the context in which we typically think about entanglement and know how to interpret it. By contrast, the covariant bound applies not on a space-like hyperplane, but on a light-like hyperplane. We can still calculate entanglement entropies on that light-like hyperplane, but perhaps there are more issues here about what those entropies actually mean. So in particular, if you're looking at an entanglement entropy on a space-like hyperplane, then physical systems can't sort of pass across the boundary on that hyperplane. That would involve moving faster than light. So the connection between those two regions is sort of clearly coming from entropy alone. Whereas in the case of a light-like hyperplane, physical systems can pass across the boundary on that light sheet, and therefore you might worry that the value we get when we calculate the entanglement entropy is not just entanglement, but also concludes contributions from physical systems literally passing across the boundary. So the exact details of how to interpret those kinds of entanglement entropies, I think, remain to be clarified. But nonetheless, it still does seem very possible that these kinds of area laws have something to do with the covariant bound. So if the covariant bound is ultimately to be attributed to area laws, how should we interpret that? Well, I think that would clearly support an epistemic interpretation of the bound. The whole point of an area law is that the von Neumann entropy or the entanglement entropy in these cases does not reflect the total ontological number of degrees of freedom. The point is that really only the degrees of freedom near the surface are contributing. We're limited in our access to degrees of freedom deeper into the region. And so there's a sort of epistemic limitation coming from the fact that the entanglement with the outside is mostly with the surface degrees of freedom. So that certainly makes the epistemic approach look more appealing. We can sort of see how that would work out in the context of limits on the entanglement entropy. Should also be noted that if that is the right explanation for the bound, that will mean the bound is certainly not an exact bound. It's going to be approximate and emergent because area laws themselves are not fundamental laws. They are approximate and emergent. So that tells an interesting story in which the bound sort of comes out as being an emergent feature of space-time that is going to appear in regimes where we have the sort of appropriate area scaling with the area laws. Another connection that you might think is important if you are interpreting the entropies as von Neumann entropies is the ER equals EPR speculation. It has been proposed that the structure of space-time is in some way going to be derived from an underlying entanglement structure. And if that is the case, then there's a sense in which the covariant bound could come out as being true sort of just by definition. Could be that the structure of space-time is defined in such a way that the entropy of a region just has to be equal to the entropy through its bounding surface, and that's where that value comes from. And now I think there are some worries to be raised here about the idea that the structure of space-time could be fully determined by an underlying entanglement structure. In particular, people working on the speculation seem to suggest at various points that it's both the metric structure and the topological structure, which is determined by the entanglement. I have some worries about that because we know that entanglement can only be created by interactions between adjacent systems, and that seems to rely on some facts about topology already. So that suggests that perhaps the entanglement structure can't define the topology. We need the topology to define the entanglement structure, but you could perhaps still say that the structure of space-time is going to define the metric structure. And since area is a metrical fact, that is going to give you kind of the result you might want in terms of explaining the bound by appeal to an ER equals EPR style conjecture. So if that were the right explanation, that would, I think, clearly support a more ontological view of the bound. in that case, we're not saying that there are extra degrees of freedom that we can't access. We're sort of saying that the number of degrees of freedom is literally defined by the entanglement structure. Great. So overall, I think up to this point, the epistemic interpretation of the bound looks more appealing to me. The ontological approach doesn't seem to have a great explanation of this apparent coincidence between the values of these two numbers of degrees of freedom on the surface and on the interior. And it also is just threatened by the possibility that we could be mistaking an epistemic fact for an ontological fact. With that said, I think things become more complicated when you take into account the role of gravity. And that's because the evidence for the covariant bound is largely based on gravitational phenomena. So if you go and look at various situations and you ask, does the covariant bound in fact apply in this situation, you find that it always does, but the reasons why it does is usually based on some kind of gravitational phenomenon. So in particular, Busso points to the focusing theorem as playing an important role in ensuring that the covariant bound is true.
Sorry,
he says,
just to clarify the terminology, I'm getting slightly lost between your way you're using epistemic versus ontological.
Yeah.
Epistemic is associated with the knowledge you have about something, whereas ontological is associated with the nature of it itself. So
that's right.
In what sense are they different in this setting? I mean, they feel the same to me, just in this setting.
In this particular setting, the epistemic interpretation would say the covariant bound reflects a limitation on our ability to access degrees of freedom of the system. So the epistemic interpretation suggests that there might in fact be more degrees of freedom inside the system than we can access from the outside, but the bound isn't telling us about those degrees of freedom. It is telling us only about what we can access. Whereas the ontological interpretation tells us that the bound counts the actual number of degrees of freedom in the system. So there aren't any additional degrees of freedom over what the bound counts. The bound is giving us the real number. So the distinction there is that the epistemic interpretation allows that there could possibly be more degrees of freedom than the ones counted by the bound.
So that's the way you're using the terminology, that the ontological counts exactly the number of degrees of freedom, and epistemic says there could be more.
Yes, exactly. Yep.
Okay, thanks.
Great. Yeah, so as I say, to this point, I think the epistemic interpretation looks quite tempting, but considering the relationship to gravity makes that complicated. So for example, Busso notes that the focusing theorem plays a really important role in protecting the bound in many situations. He notes that entropy costs energy, energy focuses light, focusing leads to the formation of caustics, and caustics prevent light sheets from going on forever. So basically, the covariant bound could not be true without the gravitational focusing theorem. The light sheets wouldn't close without the theorem, without some kind of focusing effect, and so they wouldn't have bounded entropy. So that tells us that at least some of the phenomenology of gravity can be derived from the covariant bound. If we insist that the covariant bound must hold, we can infer that something like the focusing theorem must hold. Indeed, Jacobson has famously argued that you can derive all of the Einstein equations from an entropy area relation. He's not quite using the covariant bound, but the relation he's using is pretty similar in form to the covariant bound. So, I mean, if you buy that derivation, then you're going to say that all of gravity can be derived from some kind of entropy area relation. There are some issues with the derivation, so I'm not necessarily going to support that extreme position, but it does seem clear that from the covariant bound, you can derive various different features of the phenomenology of gravity, things that must be true in order to protect the bound in certain situations.
So just to clarify, is the covariant bound meant to be ontological?
Well, I don't know. The question is it ontological or epistemic?
Okay.
Great. So the question then is, does the bound explain gravitational phenomena or vice versa? So there's clearly some relation between them. It looks like one of them is going to explain the other one. Which is it? So Churko et al. Addressed this question. They argue that it can't possibly be the bound explaining the gravitational phenomena, because they say the entropy area relation that's used by Jacobson is going to come from a quantum field theoretic calculation. That calculation gives us an entropy equal to NA/L squared, where N is the number of sort of different species present. They then show that N will cancel out due to gravitational effects, so giving us the universal bound, that universal relation that Jacobson used. So they argue it is not right to use the entropy area relation to derive gravity, because you have to use gravity in the first place to get to the entropy area relation. With that said, I think to me this looks a bit like begging the question, right? Someone who supports the idea that the entropy area relation is fundamental and explains gravitational phenomena will say, yes, this is just one more piece of evidence that indeed we can see this bound explaining gravitational phenomena. In this case, the bound has the consequence that gravity must work in such a way as to cancel out the number of species, because we have this universal bound. So it's not clear to me that just from the mathematical form of any of this alone, we can tell which one is fundamental and which one explains the other. The derivations seem to go either way, and we seem to have options there in terms of which way we want to, which one is going to be explaining the other one. So although I think the math doesn't necessarily tell you which one is correct, it is notable that starting from the entropy area relation or from the covariant bound looks a lot simpler and more unifying. The thought here is that, as Bousseau has pointed out, if you want to use gravity to explain the covariant bound, you're going to have to appeal to a whole bunch of different gravitational phenomena in different situations. And that looks kind of like, well, it looks complicated, and it looks like weirdly coincidental that all these different gravitational phenomena always come together in the right way to protect the covariant bound. It is going to be much simpler and more unifying to just sort of postulate the bound as a fundamental property and then derive these various gravitational phenomena from it. So there are at least some reasons to think that we should be explaining these gravitational phenomena by appeal to an entropy area relation or a bound rather than vice versa. And certainly if we're going to say the bound is epistemic, then at least naively it does appear that we're going to have to say that the gravitational effects are explained by the bound and not vice versa. That's because if the bound is epistemic, then we have already explained the bound as following from features of our epistemic limitations. The bound can't then also be explained by gravitational effects. So naively, at least, it looks as though in that case, the bound must explain the gravitational effects and not vice versa. But that is that is then going to have some quite strange consequences. If we're going to say that that the bound is explained by our epistemic limitations, and we're then going to say that this epistemic bound explains various gravitational phenomena, then assuming that explanation is sort of transitive, it looks as though we are then saying that our epistemic limitations explain various gravitational phenomena, which sort of suggests that gravity itself is going to end up having some kind of epistemic character, is going to be understood as something like a consequence of our epistemic limitations. And that is certainly a strange position to arrive at. Gravity, one might think, is surely ontological, if anything is. It seems quite odd to be driven towards the idea that some gravitational phenomena themselves might be epistemic in character. So this, I think, is perhaps one reason to be more cautious about the epistemic interpretation of the bound. If you really take it seriously, it does seem to lead to some quite strange consequences in terms of how we should interpret gravitational effects.
So wouldn't a fundamental theory of quantum gravity surely imply that it was epistemic?
That gravity is epistemic?
Yes.
So a fundamental theory of quantum gravity would imply that gravity is like emergent in some sense, that
yes,
it's not
exactly, yeah,
fundamental. But I don't think emergence is necessarily the same as epistemic here, because the claim that it is epistemic would say that, you know, the reason that we see gravitational effects in certain ways and not in other ways is a feature of our epistemic limitations and the fact that there's some information we are missing. So emergence is slightly different to that, because emergence is going to say that you know, all macroscopic observers of any kind would see the same effects. so it's not a fundamental property, but it is also not epistemic in most cases.
I don't quite see the contradiction there. It seems to me both could be true depending on the underlying quantum gravity. If there are many other features to it which you can only access by accessing the microstructure, then
yeah. So I do think that it's certainly possible that a theory of quantum gravity would tell us that gravity is epistemic, but I don't think it's guaranteed to tell us that. I think you can imagine scenarios in which perhaps the more ordinary case of emergence is that some feature emerges at a macroscopic scale in ways that are sort of independent of the properties of the observer in particular.
In ways that are independent of the observer.
Yes.
Yes, I would expect that that's probably true, but that doesn't mean that it was ontological still.
Well, I mean, in this case, I'm using the word ontological to refer to the idea that some phenomenon is independent of observers.
Okay.
So I mean, I think it's.
I'm thinking of the degrees of freedom of QCD emerging from a confinement mechanism, and you only have access to the macroscopic aspects of it.
Yeah.
It seems to me that it's independent of the observer, the macroscopic one, but you don't have access to all of the information, and you don't at that level. So that's why I don't see the contradiction, but maybe I'm.
Yeah, I don't think that, I'm not saying that there is a contradiction. I think what I'm trying to say is simply that I think for many people, the idea that gravity is an observer dependent phenomenon is perhaps not the way we would normally think about it. And the idea that gravity is in some sense that the phenomena that we understand as gravitational are in some sense to be explained by limitations on what we can access is, I think, not impossible. I think it's a very possible view, but it is perhaps a surprising way of thinking about gravity. Great. Yeah. So the final point was just to say that although it is perhaps counterintuitive to think of gravitational effects as being due to limitations on information access, it has been proposed by Susskind in particular that something of this kind could occur. So here I'm just going to slightly repurpose a thought experiment due to Susskind. Susskind imagines a case where we have a screen with some area A, an object behind that screen with area A prime, and both with information content proportional to their area. So Susskind notes that if gravitational focusing does not occur, then the area element on the screen is smaller than the area element on the object. And since both of them saturate the information content bound, that means that not all of the information on the area element of the screen will be able to pass through the area element on the object. We're going to have some information that's going to have to be kind of left behind and that will not make it through the screen. So Susskind suggests that we're going to find that in that situation that the perceived area of this object is going to be smaller than its real area because some of the information about its surface doesn't make it through the screen, and observing from the other side of the screen is going to sort of miss out on that information and thus perceive it as being smaller than it really is. So the thought here is that the external observer is always going to perceive that gravitational focusing has occurred, even though in some deeper in some sort of ontological sense it hasn't occurred. But in a sort of very reliable, universally applicable way, external observers will always have the impression that gravitational focusing has occurred. So this is a sort of somewhat hand-wavy thought experiment, but it gives a sense of one way in which it is in fact possible that gravitational effects could be thought of as being epistemic in origin. So although it is perhaps counterintuitive to think of those effects as being related to constraints on our epistemic access, there are possible ways in which that could come about. So just to sum up, I have distinguished two possible interpretations of the covariant bound. There's sort of epistemic approaches, which say that there could be more degrees of freedom that we just can't access, versus the ontological approach, which is, I think, perhaps the more standard approach, which says the bound is counting the real number of degrees of freedom. The epistemic interpretation, I think, to me, at least before you start thinking about gravity, looks more appealing. Once you take gravity into account, there are perhaps worries about whether you're prepared to attribute gravitational phenomena to epistemic limitations. I'm not totally opposed to that, but other people I have spoken to are opposed to it. So, and I can understand why people have that view. So that's kind of the situation I'm in. I think both of these interpretations have some plausibility. I do think it's potentially important to establish which one is right, because they are telling us quite different things about how we should understand space-time and gravity. But I'm not at this point sure which one is right. I would be interested to hear if any of you have any thoughts about which one is right. So with that, that's all I had to say. I guess we should see if we have any questions, or if anyone wants to answer my question.
Can I say something? I'm not sure if you can hear me.
Yes.
Can I be heard?
Yes, Charles, yes.
Yeah, okay. It seems to me that we're getting bogged down in some kind of semantic swamp where there's a kind of insistence that we use epistemic and ontological as words to kind of judge things by. And there are these two questions, or two properties, that gravity might have, and the entropy that we talk about and gravity might have. And if you stripped away all this semantics and just tried to concentrate on what might be true in the universe, you're much easier to discuss. You wouldn't need to spend a whole hour doing this stuff, because the meanings of the words, you can see from some of Denjo's questions, they change slightly in each slide. So, you know, if they change and get perturbed all the time, in the end, after a long discussion, it's useless, because they don't mean the same thing. That's why mathematics is quite useful. I'm not trying to rubbish everything you're saying, but you know, you have to have experiment in physics, and you have to have techniques like mathematics, but semantics is a dangerous thing that I think we're in danger of getting into the kind of discussions that followed quantum mechanics creation, you know, in the 30s and the 40s, where people couldn't agree on the interpretations. And they weren't bad, but they can consume too much time.
Well, I mean, I'm definitely in agreement with you that we shouldn't get bogged down by semantics. But, you know, I think it can be useful to use words to communicate, but to communicate what we're trying to express using mathematics. So the terms epistemic and ontological are sort of classifying terms which refer to various different types of mathematical descriptions that you could give of these situations. And for me, I think it is helpful to have those classifications in hand, because they help us think about what might be the origin of these mathematical facts we are thinking of, and how can we then pursue I think that those two interpretations suggest different routes for pursuing further mathematical developments in these areas. You know, if you adopt an epistemic interpretation, then you are potentially going to try to write down some math which could be describing the extra degrees of freedom that are supposedly missing, that we can't access. If you prefer the ontological interpretation, then you're not going to write down math describing those extra degrees of freedom. You're going to think that there's some other thing that you should be doing to study that system instead. So I don't think that the semantics in any way replace the math, but I also don't think that, you know, the math, I don't think that we can entirely get rid of words and only use math. The words are useful to communicate what features of the math are important, and to help us kind of classify possible responses to it.
Yeah, of course the words are important, but you know, I can see that you might have to have epistemic divided into 4 categories, 1, 2, 3, and 4, and you know, more categories for ontological, and then you just you're in need of something more precise.
I think what would settle the conversation would be, is there an experimental observable for the epistemic versus the ontological interpretation?
Well, kind of the point of the epistemic interpretation is that we can't access the extra degrees of freedom. That is, the point of the interpretation is that from the outside, it looks the same whether it is counting the true number of degrees of freedom or the accessible number of degrees of freedom. So there's not going to be a direct experimental observation of those extra degrees of freedom, because the whole point is that they're not accessible. With that said, I think it's very possible that there could be indirect experimental reasons to favor one or the other. For example, if you agree with Ravelli and you think that the reason people have gotten confused about the information loss paradox is because they are assuming that entropy is ontological when it's really epistemic, you will say it's very important in this case to remember that it is really epistemic, because otherwise you will run into all these confusing paradoxes, whereas the paradoxes go away when you take into account the fact that it's really epistemic. So in that kind of situation, there's not a direct observational confirmation, but there can be indirect theoretical and observational reasons to think that we should take this particular interpretation because it explains the evidence much better, or it resolves paradoxes better.
Yeah, no, that's a very good point. Yeah, I like that answer quite a lot. So if I may, is it possible that there's a middle ground between these two that would better reflect, I guess, the reality?
Yeah, so I think if you think that the bound really is counting a number of degrees of freedom, I'm not sure there's that much middle bound, because either there are more degrees of freedom than the bound suggests, or there are not. But I did sort of flag up early in the talk that the idea that the bound is counting degrees of freedom is perhaps a bit dodgy. It's not necessarily clear that's the right way to think about what the role the entropy is playing here. So if you just think the bound is not really counting degrees of freedom, that's just a sort of hand-wavy description of what it's doing, then you might think that a more accurate description of what the bound is actually doing would show that there is some kind of compromise between those possibilities.
Okay, yeah, thank you.
I think the discussion is in part whether gravity is an emergent collective phenomenon, or
Yes.
whether there is a microscopic description of gravity that needs a quantum theory of gravity.
Yes, I very much agree with that, and I think that if you believe the sort of thermodynamic approach to gravity, then that is one natural way in which you would think of gravity as being kind of epistemic in character. Whereas if you expect a fundamental, precise theory of gravity where it's not emergent, then that looks like a much more ontological story about gravity. So
I would have described it the reverse. From your discussion, I would have said it was the reverse. That the quantum theory of gravity with its own degrees of freedom was epistemic, and the one where it's an emergent phenomenon is ontological, because that's all you're getting from the entropy. There are no microscopic degrees of freedom. It's just describing these macroscopic phonon-like excitations that are there because you've got this macroscopic description, and there's no underlying quantum degrees of freedom to be described.
Well, the epistemic interpretation doesn't necessarily deny that there are underlying degrees of freedom. Both the epistemic and
the epistemic would imply that there are, surely.
Well, both the epistemic and the ontological interpretations that I've suggested here are predicated on the assumption people tend to make that the bound is telling us something about a number of degrees of freedom. If you don't think there are fundamental degrees of freedom,
they don't have to be fundamental. It can tell you about degrees of freedom that are collective excitations of something such as the phonons in a crystal are not fundamental. They're just excitations of a phonon field, which is an emergent field.
Yes, I mean, the degrees of freedom counted, insofar as the bound is counting degrees of freedom, it's counting something other than, it seems to be counting something other than just collective excitations, because the number of degrees of freedom is much greater than what you would see based on just sort of standard macroscopic collective excitations. It's possible, I suppose, that the degrees of freedom counted by the bound much smaller excitations from some even more fundamental theory. the discussion, I guess the reason people are interested in the bound is precisely because they want to be able to use what the bound says as a kind of interesting constraint on what such a theory might look like. And definitely in that case, it's important to know whether you expect the bound to appear in the fundamental theory as a sort of fundamental limit, in which case it's ontological in character, or whether you expect the bound to be something which emerges at a higher level due to our sort of limitations, because those are going to have very different consequences for how you would formulate that underlying theory.
The person who'd be able to answer the question of which one is the right one is somebody who's fallen inside a black hole.
Yes, someone inside a black hole will presumably be able to tell if there are more states there on the inside than we would expect on the outside. And so that person will be able to answer the question. Yeah.
So yeah, there you go. You've proposed your experiment. Jump into a black hole.
Yes, I'm not going to volunteer to do that experiment, but someone else is free to.
That's why we have grad students.
I
Indeed.
propose sending Elon Musk.
Oh
Yeah,
yeah.
it's a good idea. Yes.
Maybe I should just remind people that the video is still being recorded.
He's enthusiastic about traveling, so I'm enthusiastic about sending him.
Is there any other context besides entropy where this question of ontological versus epistemic shows up and is important in some way?
Yeah, I mean, like the terminology of ontological versus epistemic is also commonly applied to discussions about the nature of the quantum state. In that case, the idea is that the quantum state is epistemic if there are sort of some real underlying states that we are not able to fully know, and the quantum state reflects kind of a high-level description of what we are able to find out about those states, whereas the quantum state would be ontic if the quantum state corresponds to the real underlying state of the system. There's no sort of other information there that we're missing. So that's a similar kind of distinction. The epistemic interpretation suggests there are sort of additional kinds of degrees of freedom present that we are not able to access, and the quantum state represents the limits that on our access to those degrees of freedom. And certainly, how you interpret the quantum state is going to have consequences in terms of what kind of interpretation of quantum mechanics you find plausible, and also I think consequences in terms of how you would then expect to go on to generalize quantum mechanics to a quantum field theory and quantum gravity. So in that case, I certainly think that is an important and useful distinction. I think that in that case, as perhaps in this case, the strict sort of epistemic ontological dichotomy is a bit too strict. There may be other possibilities outside of that specific classification, but it is a good starting point for at least trying to talk about what the quantum state might mean.
It looks like there are no other questions. I think we didn't thank Emily, so we should maybe do that now.
Yes, absolutely. Thank you,
Thank you.
Emily.
Thank you,
Discussion.
Emily. That was a very nice talk.
Thank you.
We can probably stop the recording as well.
Yes, I should
Oh, yeah.
escape. Ah,
Thank you very much.
Thanks, Emily.
Cheers.
see if I can figure out how to do that. Yes.